Unit 9 is about solutions. So can you give me examples of solutions? What's the definition for solution? And can you give me examples of a solution?
Would silver nitrate be one?
Silver nitrate in what? If you have silver nitrate, if you say silver nitrate is an ionic salt, so if it's solid silver nitrate, is not a solution, is a compound. But if you add water to silver nitrate, it dissolves in water. It changes to silver nitrate aqueous. So an example of a solution would be silver nitrate in water, salt in water. That's a solution. Sugar in water, vinegar in water, right? Alcohol in water. What's the definition for solution?
An ionic compound suspended in water or an alcohol?
Well, it doesn't always have to be ionic. It could be molecular compound or ionic. It could be anything that can dissolve in water, or a solution doesn't have to be in water. Solution could be a solid in solid solution. So if you look at any alloys that is mixture of two solid, that's also solution. In general, anything that is a uniform mixture or homogeneous mixture, the other name for a homogeneous mixture is called solution. Solution can be solid in liquid, can be liquid in liquid, like when you have ethanol in water, that is a liquid in liquid solution. If you have vinegar in water, that's liquid in liquid. You could have gas in liquid. Can anyone give me example of gas in liquid? Solution of gas in liquid. Gas in liquid is like soda, right? Carbonated drinks are all gas in liquid. When you have a solution, solution is mixture of solute and solvent. What part of the solution is considered or defined as a solute is the one in greater amount. So you could say if you have 90% water, 10% salt, so 90 grams of H2O plus 10 grams of NaCl. Then you have NaCl solution, it's an aqueous solution. Sodium chloride is going to be the solute because of the quantity is lower, and water is going to be solvent. But if you have 60 milliliter of ethanol plus 40 milliliters of water, in this case, ethanol would be the solvent because the 60 milliliter, and water would be solute. So the one in greater amount would always be solvent. The one in less amount is going to be solute. Okay, so if they are in the same state, the major component is the solvent. That means the one in greater amount. With those examples, hopefully it helps the definitions. Some of the items are repeated in this. I just wanted to show you the picture. The substance present in greater amount is the solvent, and the solute is the substance present in the lesser amount. And the solution is uniform. Solution is a uniform mixture. Means if you pass it through filter paper, there should be nothing left on the filter paper. Solution is transparent. So if you take a piece of paper that has a writing, keep it on the other side of the solution, you should be able to see the writing through the solution, because solution is transparent for the liquid part. If it's solutions with the liquid solvent, they are transparent. Solution of gas in gas, like air is a solution. Air is a solution, and the components of the air is like different you have oxygen gas, nitrogen gas mixed together, 78% nitrogen, 21% oxygen, and then you have 1% of everything else mixed in the air, and you can see through. Is homogeneous. So if you take one part of the air, then it's all homogeneous. Then you have a solution. How does solution form? A solution form between solute and solvent, basically using the general rule of like dissolves like. So if the compound is an ionic compound, okay, this ionic compound is going to break down to ions, and then you have, we talked about intermolecular forces already. So we have the ion dipole. So if you have the water molecule separating sodium ions from chloride ions, water molecule from the oxygen side, which is negatively charged, is going to surround sodium ion because sodium has a plus charge. And then chloride is negatively charged. Water molecule from the hydrogen side is going to surround and attract the chloride ion. So you get these two sodium and chloride ions separated from each other by the water molecule, and that means solution, formation of the solution. So solution of this ionic compound is going to form because it's separated to ions. And if you have like a sugar that is a polar compound, it dissolves in water. Polar compound of sugar, you see you have so many OH bonds, and all those OH bonds can form hydrogen bonding with the water molecule, and is going to be attracted by the water molecule. So we have the solution as soon as it turns to a uniform mixture. For a non-polar compound, like when you add oil to water, oil has dispersion forces, water has hydrogen bonding. It's not going to dissolve, and it forms two separate textures. You see that is not uniform. This area of the mixture is different from this area of the mixture, or this area of the mixture, and is not uniform. So you have a mixture, but it's not solution. It doesn't have to be always water. Like if you have a container of oil and then you add salt, it's going to settle down and is not going to dissolve. So if it doesn't dissolve, there is no solution. You could see the salt settle down at the bottom of the oil, and then you have the oil, and is not the solution. It's again a mixture. The solution as a mixture can't have different or variable composition. Means that you could have 5% NaCl solution. So if I say NaCl AQ, that means NaCl solution. You could have 10% NaCl solution. Okay? When you say salt water, you cannot say, that there's only one salt water. You could have salt water that tastes more salty than the other water. You could have 15% NaCl solution. At room temperature, if you put 40 grams of NaCl in water, what's going to happen? In 100 grams of water, 40 in water to make 100 or 100 milliliters. So I'm going to put in 100 this. What do you think it will happen? We know that if you add 1 spoon of salt, it would dissolve. 2 spoons of salt, 3 spoons of salt, it would dissolve in a cup of water. What happens if you put 40 grams of water, of salt, in 100 milliliter water? What do you think can happen? You think all of it would dissolve?
Yes.
What other information do you need? The other piece of information you need is to know that at room temperature, okay, at room temperature, solubility of sodium chloride is 34.5 gram per 100 milliliter. If I give you this information first, you probably would say,
With that information, all of the salt wouldn't dissolve in the water.
Wouldn't dissolve. Okay. With this information, now your answer would be no, some of it dissolves in water, because that when you say solubility, this number shows the solubility. Okay. At room temperature. 34.5 grams of it would dissolve. And what happens to the rest of it? The rest is going to settle down. So you have some salt in the water and then some salt left over. How much of it is going to be left over? About 5.5 grams of salt is going to stay, and 34.5 grams of it would dissolve. There are some factors that can increase the solubility. If you notice, 2 times I repeated this is at room temperature. Okay. What happens if I increase the temperature to 50 degrees Celsius? What do you think will happen with this 40 gram?
Solubility will increase.
Solubility would increase. Very good. We don't know exactly if all 40 gram would dissolve at the higher temperature, at the 50 degree temperature, or some of it would dissolve. All we can say that more than 34.5 gram would dissolve at 50 degree, because this is at room temperature. We do need more information to say how much it would dissolve. If someone would tell me that at 50 degrees Celsius, 39 gram would dissolve in 100 milliliter, basically solubility is 39 grams, then I can answer the question and say, okay, out of 40 gram, 39 gram would dissolve and 1 gram would be left over. But I need, and you need additional information, right? Okay. So we know about the solution. We know that it's going to have variable composition. Pure substances, they have constant composition. That means when you say water, pure water only water and it has only water molecule. Anywhere of the container that you reach is water molecule and it's pure substance, so it has a fixed composition. But if you have a mixture of salt water, you could have different concentrations. So when we are talking about a solution, then we have to give a little bit more information. We have to say, is this solution, okay, saturated? Is it high concentration? Is it low concentration? Is it dilute solution? Is it saturated? Is it supersaturated? And for that, for dilute and concentrated, that's like very subjective, and you should know that. If you have like a sweet tea, that, you know, it tastes sweet, too sweet to you, it may not taste too sweet to someone else. Or salt water, dilute, but in general, you could still give a definition. When a small amount of solute is dissolved in solvent is dilute. Concentrated, when large amount is it dissolves in water or in the solvent, is concentrated. Again, it's subjective, it's not exact number. If maximum amount of the solid or solute has dissolved in solvent, that is so that solution is called a saturated solution. With the example that we had before, if we have 34.5 grams of salt in water, in 100 milliliter of water, at room temperature, then we have a saturated solution. If we have 5 grams of salt, we add 5 grams of the salt to 100 milliliters of water. What happens if you add another 2 grams of salt? It would still dissolve. It would continue to dissolve. Since it's going to continue to dissolve, the solution that we have at that point is unsaturated because it still can take in more. So if you can dissolve more of the solute, is unsaturated. If it reaches the maximum, that means you don't have enough water molecule to separate the sodium ion from the chloride ion. Then you have a saturated solution. And if anything extra you add, it would settle down and it would be, it remain as a solid because it doesn't dissolve. It would stay as an undissolved portion of the solid. So this diagram here in this picture, it shows that if you have leftover solid, that would be in equilibrium, or it's called dynamic equilibrium. The solid piece of solid can go to liquid as long as a solid from liquid goes down and precipitates or forms the solid or crystallizes. So this can go back and forth. That's why it's called equilibrium. So if you have leftover salt, it can go back and forth, but for every molecule that goes into the liquid in aqueous form or it dissolves, one should go down and it should never exceed the maximum allowed at the given temperature. Any questions? We talked about dilute solutions, having small amount of the solute, and concentrated solution having larger amount or large amount of the solute in a given solvent, but it doesn't give exact number. But quantitatively, if you want to talk about stoichiometry of the reactions, and then you want to know exactly how much salt you need to add to the solvent in order to make the solution, you have to have exact numbers. So the numbers should be given to us. What concentration exactly do you want the solutions to be made? Some factors that affects the solubility, as we talked about, is the temperature. You increase the temperature, solubility would increase, and that's like majority of the time. There could be some exceptions, but it's not, common. Solubility of gas in liquid. When you buy like a soda, and when it's cold, you pour it into glass, a jar or a container, a glass. You see like some bubbles forming on the side of the glass. What does it mean? Means that when it's cold and under high pressure, the carbon dioxide would stay in the container or in the solution. When you open it, when you pop a soda can, you see that fizzing sound. Some of the gas would come out because you're not letting it go. The pressure is decreased now, so gas molecules would leave the liquid. Also, temperature, if you increase the temperature, if you place it in a glass and then leave it at room temperature, you would see bubbles forming in the glass. That means those gas molecules are coming out of the liquid and they attach to the wall of the glass. So solubility of gas in liquid does not follow the general trend. This is often for solid in liquid, but for gas in liquid, the lower the temperature, more gas would be dissolved. And the higher the pressure, more gas would be dissolved. Okay. To have a exact number, or we have to have a unit for our concentration that is going to express the exact amount of the solute in the solution. One of those concentration units, it can be percent, which is like a mass volume percent. So if you say 10 gram of salt in 100 milliliter of solution, so this is the volume of the solution, 10 gram of salt, that means 10% mass volume solution. So that's one of the units, the amount of the solute in amount of the solution. Parts per million is like how many gram in million gram of water, or how many milligram in kilogram. Okay, it's the same thing as the ppm, milligram per kilogram. Parts per billion, when do they use parts per billion? Is like if they're talking about the pollution of the air, like a percentage is going to be a huge number. Nobody would be able to live in that under that situation if there is like a a percentage of the air. If they express in percentage, that would be like very, very low number. Again, it's hard to work with. And or let's say if they want to find the water quality and they want to find out how much mercury is in that water, hopefully is in the part per billion, because if it's a higher number, it's going to cause cancer to most of the population and it's very dangerous. Like if you have high concentration of lead or mercury in water. So the unit that is used is very small number, or it expresses very small number, and we still want like workable number. We don't want to say like 0.0000 milligram in kilogram. So instead, you would say part in billion. Molarity, it's number of moles per liter of solution. So in a chemical reactions, quantitative analysis of chemical reactions, we use molarity because we need to know number of moles. For those, we cannot use percentage. Percentage is used like in the lab if you want just the approximate concentration. You want like you want to make a solution acidic or basic, only you would use 10% HCl or 10% sodium chloride, add few drops until it reacts to litmus paper. But when you have quantitative analysis that you want to do titration, you have to know the molarity. You never do titration with the 5% or 10% acid. You do with 1 molar, 0.1 molar, 0.2 molar, exact molarity or concentration of the solution expressed in mole per liter. Okay. When you're talking about the mass volume percentage, I posted another PowerPoint in the in D12 that has a lot of examples for you for problem solving, because I wanted to make sure I can finish the unit. Today, I did not put a lot of examples here, but examples are included in the other PowerPoint. So please refer to that. And the solutions are there. It's not just the problems. It's the problem and then the solutions. So to find the percent or concentration based on the percent for a solution, you must be given mass for the solute and the milliliter of the solution. So if you add 8 grams of sodium chloride into water, okay, you add plus H2O, you dissolve it and add enough water to make 400 milliliters. Now, what would be the percent? The percent, to calculate the percent or mass volume percent, is going to be gram of the solution, 8, gram of the solute, 8, divide by the 400 milliliter. This is to make 400 milliliter solution. We are not adding 400 milliliter water. That's different. When you make enough, you make a solution first and then dilute it to 400 milliliter. So you add enough water to make 400 milliliter of solution, because by definition you need the milliliter of the solution. You don't need the milliliter of solvent for the percentage. Times 100%. Okay. So this is going to be 2%. So that's how you calculate it. Mass of the solute divided by milliliter of the solution times 100. If they tell you that you have how many grams NaCl is present in 250 milliliter of 5% solution. If you have your calculators, you can start doing the calculation and tell me how much of that salt is going to be if you have a 250 milliliter solution. So let you have 250 milliliter here, and the solution is like 5%. How many grams of NaCl are there? What should I do? Trying to find out how many grams of NaCl.
First divide by 100% on each side.
Okay, it would be easier. So you could do like proportion, or you can use as a conversion. When you have the percentage, if you use conversion, it's going to be very easy. It's going to make your job much easier. So you can write a 2 conversion factor based on 5%. One conversion factor would be 5 gram over 100 milliliter of a solution. SOLN is abbreviation for solution. I'm going to write that. Or you would say 100 milliliter of solution over 5 gram. So these two are conversion factors. If I call this conversion factor A, conversion factor B, what is other given information for me? So this is the fact, the given information is 250 milliliter. So I can start with the 250 milliliter and multiply by one of these conversion factors. Which one should I convert? Which one should I use, A or B? A, because I want to cancel the milliliter. So 100 milliliter, 5 grams. Then I would cancel the milliliter. And it's going to, then I do the calculation. Okay, so 5, is this 12.5? 12.5 grams of NaCl. So I have 12.5 grams of NaCl in 250 milliliter of 5% solution. Any questions about this calculation?
No, just 1 second so I can get this down.
This is going to be, it is recorded, so you will be, you will have access to it. Okay, perfect. It's 12.5. Great. Okay, next, see what's next. How many grams of sodium hydroxide needed to prepare 75 milliliter of 14% solution? So we have the example, 75 milliliter and the 14% is given. I would get the 2 conversion factors. One of the conversion factor is 14 grams over 100 milliliter, and then the other one is 100 milliliter over 14 gram. Since the volume is given and the mass is asked, I'm using the conversion factor that cancels the volume and converts to mass. Do the calculation for the numbers and then report with proper unit, which is 10.5 gram of sodium hydroxide. Any questions about this? So if the solution is given, if the percent is given, you can find out how many grams it's going to be. If the percent is the question, you can also make that based on the conversion factors. Next unit is molarity for solution. That's another concentration unit. And when you express the concentration of solution based on molarity, when you say 1 molar, that means for every liter of solution, there is 1 mole. When you say 0.1 molar, that means if you had 1 liter of that solution, there would be 0.1 mole of that solute in there. So it's the number of moles of solute in liter of solution. And because we want to make the solution or the volume of the solution that includes the volume of the solute and the solvent, first, we are going to do the calculation first on the paper. How much do we need? So if we need 1 mole, we are making 1 molar. This is this picture shows 1 molar solution of NaCl. Then we need to take our periodic table out and say NaCl mass for sodium is 23 in the periodic table, and then Cl is a 35.5. If I add these two, it's going to be 58.5 gram per mole. So then I bring a balance, and then I use the balance pan. I add enough salt to show 58.5 gram. That salt then is transferred into a volumetric flask. Okay, volumetric flask has a index line that if you fill the solution, if this container to this line, is going to have exactly 1 liter. If you are using the 1 liter container. So you're going to add the salt first, add some water, dissolve it, then add enough water to make it the mark. With this, you're not adding 1 liter water. You're adding enough water to make 1 liter solution. Okay, I hope you see the difference. Okay, you add enough water to make 1 liter solution. And you have to first start with molecular formula of the solute. Read the problem. How many moles of that solute you need? In order to find that many moles, you need the molar mass. So you get the molar mass. And from the molar mass, you calculate how many grams you need for the looking for number of moles. So let's see, in this example, this example is cut off. Okay, find the molarity of a solution that has 25.5 gram of potassium bromide dissolved in 1.75 liter of solution. What would be your starting point? Because we want to find the molarity, we write the formula for molarity. Molarity, or capital M, equals number of moles per liter of solution. So this problem, it gives me the liter already. So I know that this is 1.75 liter for the solution. But in order to find the molarity, I need to find number of moles. How do I find number of moles? Do I have number of moles? No, I am given the gram. So if I'm giving only the gram, then I have to look for periodic table and find the molar mass for KBr. I think potassium is 39, right? Potassium bromide, potassium is 39, and this one is 80. Okay, 39 plus 80, it gives me 119 grams per mole of KBr. So first, find number of moles. So to find the number of moles, I need to say, or start with the 25 grams. 25 grams times 1 mole of KBr over 119 gram of KBr. That gives me the number of moles. When I have the number of moles, I divide by the liter of solution, and that gives me the molarity. Any questions about calculating molarity? It's very important for you to be able to calculate molarity or find how many grams you need to make that molar solution, or how many liters of solution you can make. Because the question, you see that there are 3 components. One is the liter of the solution. Second is the mass of the solute. Third is molarity. Out of these 3, any 2 is given, you should be able to calculate the third one, knowing that you always have access to periodic table. That's why on the exams, they don't give the mass for each one, they give you a periodic table. So you should be able to use the periodic table to find the molar mass. So for molarity problems, mass of the solute could be a question. Number of moles of solute could be question. Liter of solution could be question, or molarity could be question. But as long as you know the formula, you know the base, molarity is number of moles over liter solution, you should be able to find the number of moles, or if you have the moles, find the gram and answer the question. What does 2 molar solution means? 2 molar solution of a sugar. It means that if you have 1 liter of the solution, there would be 2 moles of that sugar. How many gram is that? I don't know. Find the sugar, formula for sugar, find the atomic mass for each of the elements in the sugar, add them all up to get the molar mass, and then you multiply the number of moles by molar mass to get the gram. Okay. So if the sugar solution concentration is 2 molar, what does it mean? It means if you have 1 liter solution, it would be 2 moles. Half a liter solution would be 1 mole. 2 liter solution would be 2. So molarity just shows the ratio and the relationship. You don't always have to have 1 liter of solution to work with. You could have like 5 milliliter of solution, but still concentration is 2 molar. What does it mean? It means that if you had 1 liter of that solution, it would have contained 2 mole of that sugar. So it's a ratio that we are working with. Questions? No questions? Okay, let me see if I can get this. Okay, how many liters of 0.125 molar sodium hydroxide contains this many moles of sodium hydroxide? Can you give an answer without solving this problem? What does 0.125 molar means? My question. Okay, What does 0.125 molar means? It means if you have 1 liter, it's going to contain 0.125 moles. 0.255 is almost, it's 2 times this value, right? It's almost 2 times the value. So it's going to be 2 liters. So every liter is going to have that value. And you can change that to ratio. So you would say 1 liter of solution is going to have 0.125 moles. You could have the other conversion factor also, 0.125 over 1 liter of the solution. But in this example, we want to cancel the moles of solution. We want to come up with the liter of solution. So we are using this conversion factor. So molarity can also be used as conversion factor because it shows the relationship. It shows the ratio. So if you want 0.255 mole, you multiply by the conversion factor to change it to the liter. So it does make sense. So 0.250 would be exactly 2 liters because it's a 0.255 is a slightly higher than 2 liters. A stock solution is a solution that has high concentration. They usually make this in the lab, they leave it, and then when they want it like lower concentration, they just dilute the solution. To dilute a solution, the formula is used M1V1 equals M2V2. Let's say you have a cup of iced tea and this is too sweet for you. Okay, you have a cup of iced tea and it's too sweet for you. You ask for some water and you add some water, you dilute it. Okay, and if you dilute it, what's going to happen to the sugar, the amount of the sugar that was in the iced tea? Would the gram of the sugar or the amount of the sugar that was in that iced tea change? Or just the taste would change? Would the taste change or the amount of the sugar?
The taste.
The taste only changes, right? The amount of the sugar, because you didn't take sugar out of the container, you just added more water. So the taste does change only. How much sugar is there now is the same amount of sugar you had before. Okay, and if the amount of the sugar was expressed in number of moles, then number of moles before adding water, before diluting, and after diluting is going to be the same. How do you calculate number of moles? When you say molarity equals number of moles, divide by liter of solution, you can rearrange this formula and say number of moles equals molarity times volume in liter. Volume in liter. So when we say molarity, we express that as a M1, molarity before mixing or before dilution. And then volume is like a V1. So we have M1, V1. Molarity times volume before mixing. This is the number of moles before mixing. Before diluting. And this is going to be number of moles after diluting. Or after mixing with water. If you add the volume, molarity would go down because the taste, when you add water to the iced tea, the taste changed. The taste was less sweet. So molarity would go down. And this formula is true anytime you add water to dilute a solution. When you have a stock solution as high concentration and you want to make dilute solution, you add water. But you want to know exactly how much water you need to add, and you want to know other, calculation. So you would use this formula to do the calculation. I have an example here on the next slide for you. Let's say, okay. What volume should you dilute a 0.2 liter of 15 molar sodium hydroxide solution to make 3 molar sodium hydroxide solution? First step, you want to label all your numbers. Recognize that this is a dilution problem. We know that we are going to use a M1V1 equals M2V2. We know this. So now, what is your M1? What is your M2? You have to read the question or information given in the question carefully in order to find out these values, which one, label them. It's very important to label. 15 molar going to 3 molar, so 15 molar is from basically 2. So I already know the value for M2 is 3, and the value for M1 is 15. So my M1 is 15 times, volume is a 0.2 liter, because it's saying it's a 0.2 liter of the 15. So 0.2 equals, have the M2, which is 3 times V2. The units, they must be the same on both sides. So if I get liter for this, the volume that I'm going to calculate is going to be in liters. If I have milliliters, the volume that I will be calculating, it would be in milliliters also. So you're going to divide both of these by 3. And then you calculate the V2 equals, but the main thing is to make sure that you label these. So you have V1, you have M1, you have M2, and you need to find the V2. So V2 is going to be 1 liter. So 5 times dilution is going to go from 0.2 to 1 liter. How much water should you add? Because some question could ask you how much water should you add. You already have 0.2 liters. In order to change it to 1 liter, you have to add 0.8 liters. But this question, it was nice to you, and it's just asking you what volume should be diluted to. So this is the final volume. If the question asks how much water, you would subtract the initial volume from the final volume, and you say 1 minus 0.8 is going to be, 1 minus 0.2 is going to be 0.8 liter water should be added. So number of moles equals molarity times volume. So if you have the molarity and the volume for reactant, you know the number of moles for reactant. On the product side, you can find the number of moles for the product based on number of moles of the reactant from balance equation. So this calculation of the number of moles for the solution, you can use it in the stoichiometry of the reaction as well. So in the solution stoichiometry, because before we were talking about pure sample, and you said if you have the mass, convert the mass to mole, and then mole of the reactant to mole of product, and then answer the question. If you have a solution, all you have to know, or the only difference is that in this case, number of moles is not mass over molar mass. Number of moles is molarity times volume in liter. That's the only difference. So if you have the volume of the reactant and you have the molarity, you can get the moles of reactant. So you must have the molarity in order to convert the volume to moles. If you have the moles of reactant, you can find the moles of product, and then you could get the volume of the product. So in solution stoichiometry, just like other stoichiometry, regular stoichiometry, you must have a, what did I do? In solution stoichiometry, you are given the volume and the molarity. That's just like you're given the number of moles for the reactant. Okay, so let's look at this problem together. What volume of 0.15 molar KCl is required to completely react with 0.15 liter of this molar in the reaction? So we have to look at the balanced equation and what is given to us. Okay, what's given is the item that you have both volume and concentration. In solution stoichiometry, you don't have just, if the volume is given, is not a given, is not known. The known would be the one that you have both volume and concentration. So required to react with, for lead nitrate, I have both volume and I have the molarity. So if I have both volume and molarity, I know that lead nitrate is given. What I'm looking for is KCl. For KCl, molarity is given, volume is not given. So I have to find number of moles of KCl first. So what would be my first step? My first step is to find the number of moles of lead nitrate, because that's the only one I have enough information for. How do you find the number of moles for lead nitrate? Can you tell me one more time? Even the solution is here. I want to find number of moles. What should I do? Number of moles. And in this case is for the lead nitrate. What should I do to find number of moles? I'm waiting for your response. Number of moles. Number of moles is molarity times volume in liter. So I hope you remember next time I ask you, how do I find number of moles of solute in a solution? You need the molarity, you need the volume. Okay. So number of moles for lead nitrate is going to be volume times the molarity. Okay, that gives the number of moles of the lead nitrate only. So when I have number of moles for lead nitrate, then I need to find moles of KCl. How moles of lead nitrate and KCl are related? For every 1 mole of lead nitrate, I need 2 moles of KCl. So if I have moles of up to here, I have moles of lead nitrate. And then I multiply by 2. How do I find this 2? This is coming from balanced equation, is the mole ratio. 2 moles of KCl for every mole of lead nitrate. So I have, in this step, I have the moles of KCl. So if I have moles of KCl up to that step, then I need to find the volume. You can do this in multiple steps, but if you know that you have the number of moles, if you have number of moles for KCl, what other information you need in order to find the volume? If you have number of moles for KCl, you have the molarity for KCl, and you find the volume for KCl. You can rearrange this formula in the couple different ways. You could say volume equals number of moles divided by molarity. Molarity is number of moles divided by volume, and number of mole is molarity times volume. So from the balanced equation, you find number of moles using the ratio from balanced equation, you convert the moles of lead nitrate to moles of KCl. And when you have moles of KCl, then you would find the volume, because for every liter, we have 0.15 because the molarity was given to us. That gives you the volume for KCl. In the solution, if molarity is given already, you can find the number of moles using the volume. You don't need the molar mass. I'm sure you have a lot more examples in Newton assignments, and then the other PowerPoint has more examples also. But try to use the worksheets, the Newton worksheets for this chapter, and review all the examples. The more examples you do, the faster you get for these calculations. One other aspect about the solutions for ionic compounds, when they dissolve, they change to ions. And if lithium chloride, it dissolves in water, you add water, is going to change to lithium ion, AQ, and chloride ion, AQ. If calcium chloride dissolves in water, is going to give you 1 calcium ion, AQ, and 2 chloride ion, AQ. So just pay attention also to this. If you have 1 mole of calcium chloride, it can give you 2 moles of chloride ion. Be careful with that one. Okay, some examples. We covered the theory already. These are some of the examples. Which of the following solid would dissolve in water? Would gasoline dissolve in water? Or why gasoline doesn't dissolve in water? It is based on the polarity, right? Like dissolves in like. Yes. Gasoline is nonpolar, iodine is nonpolar, HCl is polar, and sodium sulfate is ionic. Anything that contains sodium of ionic compound is soluble in water. So if you're asked for the solubility of these compounds, then you can say, just decide that is ionic and it contains sodium, so it's soluble. Gasoline is nonpolar, not soluble. Iodine is nonpolar, is not soluble, but HCl is polar and is going to be soluble. Another example, what happens if the salt disappears when you put in the water? How would you declassify that? Would that be saturated or unsaturated? If it's still taking salt, that means the solution is unsaturated. So the colored text here is actually the answer. But for the other PowerPoint, you have the questions and answers separate in separate slides. But when you add sugar to a cup of water that does not disappear and it sits at the bottom of the cup, that means that solution is already saturated. Okay. And could a carbonated drink explode when you leave it in the hot sun? What happens to the carbonated drink if you leave it in the hot sun? Where the solubility of the gas is higher at high temperature or lower at the high temperature? You can answer that part.
Be lower.
Solubility is lower. That means it comes out of the solution. And if it comes out of the solution, it doesn't want to stay in the liquid, in the solution, in the soda, then it would put a lot of pressure to the wall of the container, and that's why it's going to explode. If the water is too warm, fish would die. And the reason for that is warm water does not hold enough oxygen gas, because solubility of gas in water decreases as you increase the temperature. So if you warm up the water, all the gas is going to go away. And if you experience this at home, you have like pot of water and you put it on the stove. Before it starts boiling, you would see like some bubbles. And those bubbles are the gas molecules that they were dissolved in the water. Now they're coming out. But when it reaches the boiling point, the water would vapor. But at the beginning, it just comes out. Or if you have cold soda, you put in the water in a glass and leave it on the table for 2 minutes, you would see bubbles are forming on the side, the wall of the container. Open can would have the soda would get flat when you open the can, is because of the pressure. Solubility of gas is higher at high pressure and lower at low pressure. So if you open the can, you lower the pressure, solubility decreases for the gas. That means gas comes out of the solution. It doesn't want to stay in the solution. And the solution that loses all the gas is going to be flat. Okay, these are some practices that we already use, the writing of conversion factors. If you have any questions, let me know. We already solved this problem to prepare. This is like diluting. You follow the instruction, then you add water. This is stock solution, and that's how they sell like concentrated orange juice. You add water, you mix it well, and then you have dilute. So in dilution, water is added, volume would increase, concentration decrease, but the mass of the solute, the same example I used before for sugar in iced tea, the mass of the sugar does not change. Mass of the solute does not change. C1, V1, C2, V2, that's used for concentration, expressed in percentage. M1, V1 is the concentration expressed in molarity. So it's the same thing, same formula is used for dilution problems. If you dilute a solution, diluting 10 milliliter of 9% to 60 milliliter. What would be my first step? What should I do first? The formula used is C1 V1 equals C2 V2. I have to label the information given according to this formula. I know that 10 milliliter is going to be V1, 9% is going to be C1, 60 milliliter is V1, then we have to find C2. So in order to find the C2, I just plug in the numbers. 10 times 9 equals C2 times 60. And you divide both sides by 60. 90 divided by 60, that would be 1.5. And then C2 is going to be 1.5%. Any questions?
I'm sorry, I don't have a question. That was V1 and V2 and are both V1.
Okay, I said that I had a V1 and here in the purple area, it shows the numbers also. V1 was the 10 milliliter, V2 was the 60 milliliter, and then C2 was unknown. So we're trying to find the two.
Okay, because I heard you said V1 and V1. I was wondering. All right,
I'm sorry, it's my fault, sorry.
Okay, thank you.
You're welcome. Okay, dilution factor is like how many times you're increasing the volume. That would be basically dilution factor. If you double the volume, that's 2. Dilution factor is 2. And if you double the volume, concentration would be in half. And then 4 times if you increase the volume to 4 times the volume, then the concentration would be 1/4, basically. Okay, one definitions that we have for the colloids, the difference between the colloids and the solution. In the solution, particles are very small, they never settle down. You have a solution of salt water, it would stay as in solution like for days, it doesn't settle down. And then the colloids, the molecules are larger, or they are a group of molecules or ions. The particles do not settle down, but they are kind of moving around. Particles can be separated by filters. I mean, by semi-permeable membranes, sorry. That's just the, for colloids, the particles is not large enough to separate by filters. Solutions is not going to be separated by cannot be separated because it's homogeneous mixture and the particle size are small. And suspensions, those are the mixtures that you have large particles and they can be separated by filter, okay? And they settle down quickly. You do have some examples also. It's just more of examples. For the colloids. And definition for colloids, or another example, like a sample question for colloids, like a mixture that has solute particles that do not settle out, but are too large to pass through semi-permeable membrane, is colloid. That means you can separate them by the semi-permeable membrane if it's too large to pass it through. We talked about 2 units for the concentration, molarity and percentage. Any questions that you might have? The last few slides, they were just more of a review of what we covered before. Okay, perfect. Okay, one last question, example for the solution. You want to find the molarity of of 5.86 molar ethanol solution. Density is 9.927. Well, we did not talk about molality yet. Molality is different from molarity. That's another unit for the concentration. Molality is number of moles of solute in kilogram of solvent. Remember, I said when you are making molar solution, you have to first make the solution, add water until reaches to like the volume that you wanted. So that means the volume of the solute is included in the volume of the solution. But when it comes to molality, which we show with the lowercase m, not a capital M. So when you see capital M, that's for molarity with an R. Lowercase m is molality with an L, okay? Molality. In molality, you still need the number of moles of the solute, but instead of volume of the solution, you are using mass of the solvent. So how much of the solvent was used? So if you use this formula, you need the mass of the solvent. You need the moles of the solute in order to find the molality. So with the next example, molality, they're very similar. So you have to be careful when you're reading this, like molality, which is lowercase m, you're trying to find lowercase m. So if you're trying to find the lowercase m, what information we need? We need number of moles, and we need mass of the solvent. Need number of moles, need mass of solvent, okay? Mass of solvent. How do you find number of moles?
So volume times molarity.
Very good. Molarity times volume, that gives you the number of moles. So if we assume that we have, 1 liter of the solution, right? If we assume we have 1 liter of the solution, then is going to be, for 1 liter, is going to be 5.86 molar, right? So number of moles, since you said the formula correctly, I'm going to use that. Number of moles equals 5.86 molarity, which is the mole per liter, times 1 liter, which is the volume. So number of moles equals molarity times volume. So we find the number of moles based on molarity times volume, and it's going to be 5.86 moles. The liter would cancel with the liter. Very good. So if we have 5.86 moles of ethanol, how much ethanol is going to be? Then we have to multiply this by 46 to get the mass of ethanol. Okay. So we need the mass of solvent also. What is the mass of solution? Mass of solvent is going to be mass of solution minus mass ethanol. That makes sense? Mass of solvent. So we need moles and we need mass of solvent. Okay, we already have the moles. We found the moles here. We need the mass of solvent. In order to find the mass of solvent, we need the mass of solution and we need mass of ethanol. How do we find mass of solution? Volume of the solution is 1 liter and the density is 0.927. So mass of solvent is going to be 1,000 milliliter. Should I write it like 1,000 milliliter times this? I have it right here. Okay, that gives the mass of solution because we assume 1 liter and 1 liter is 1,000 milliliter times density. Volume times density, that gives the mass of solution. So we have mass of solution as 927 minus mass of ethanol. How do we find mass of ethanol? We have the moles of ethanol, but we need the mass of ethanol, and that would be 5.86 times 46 gram per mole. So this is mole, gram per mole. Mole would cancel with mole. And how do I know this is the 46? That's 2 times 12 plus 6 times 1 plus 16. That gives you 46 gram per mole for ethanol. So mass of solvent is coming from here. We need the mass of solvent. You subtract these two. So this adds up to 270. We are looking for mass for solvent. And that equals 657 gram. And 657 gram is the mass of ethanol. So for molality, to find the molality, we need the moles of solute, which we have 5.86 because the moles, number of moles doesn't change. We need the mass of solvent, but in kilogram. I found 0.657 gram. We have to divide by 1,000 to change to kilograms, so that would be 0.657 kilogram. So moles of the ethanol divide by kilogram of solvent, or mass of solvent in kilogram. And that gives you molality with an L. Molality is not used in 1045 often, but when you go to 1046, if you were expected to learn this in 1045, then at least you have heard about it, but it's not used often for the calculation in 1045. We do use it for colligative properties. Colligative properties, like when there is a change in temperature of solution, like when you add solute to solvent, and there is a freezing point depression or boiling point elevation. In those cases, we use molality, which is number of moles divided by kilogram of solvent. Okay.